He is Associate Professor of Radiology and Radiological Science, Johns Hopkins University. The title of his paper is ASL-based MRA.
Okay, thank you for the introduction. So my name is Chin Chin from Johns Hopkins University. Most of the slides were prepared by Dr. Yoriko Suzuki from Oxford. Unfortunately, she could not be here. So ASL-based MRA can be implemented for 3D static MRA, 4D dynamic MRA, and viso-selective MRA. I will describe various labeling approaches, including spatially selective ASL, such as pulse ASL, pseudo-continuous ASL, as well as velocity selective and acceleration selective ASL. As ASL typically label and control two acquisitions and then do the subtraction, I will briefly discuss scan time and strategies for reduced scan time in the end. In perfusion imaging, the SNR differences between Picasso and pulse ASL is rather obvious, and Picasso has been the recommended labeling approach for perfusion imaging. But both pulse ASL and Picasso are very useful for dynamic ASL angiography, and the choice of the labeling may depend on what your application is. For example, in pulse ASL, a single RF pulse inverts all spins within a large area of RF coverage, and the readout can be started shortly after the labeling pulse. So, the pulse ASL is more convenient to visualize a bolus of the labeled blood flowing into the vascular tree in a dynamic 3D angiography. However, because RF transmit coverage is limited, the thickness of the labeling flap and the resulting bolus duration will be also limited. So, pulse ASL is not suitable for static 3D angiography. In contrast, Picasso's long labeling duration is more convenient for visualizing the whole arterial tree in a single phase for static 3D angiography. Additionally, a hybrid of Picasso and the pulse ASL was also proposed for the static 3D angiography, in which a long Picasso labeling generates labeled blood enough to fill the whole arterial tree, followed by a Picasso labeling avoiding the signal loss in proximal vessels caused by fresh unlabeled blood flowing into the imaging volume during the post-labeling delay. Let's get back to the dynamic angiography. Now, Picasso's long labeling duration is not very convenient for visualizing the inflow of labeled blood in early phases. As you see, even in the first phase, acquired immediately after the end of the long labeling, the labeling blood has already reached the distal arteries. Therefore, each early inflow phases cannot be visualized by the normal subtraction. However, there is a solution called inflow subtraction. Assuming a very long Picasso labeling, the arterial tree can be fully filled by labeled blood in the first phase, and in the second and later phases, non-labeled fresh blood is flowing in. By subtracting these later phases from the first phase, the early inflow phases can be generated. However, it should be noted that the whole arterial tree should be filled by the labeled blood in the first phase. Any delayed arrival in the distal arteries will not be visualized by this inflow subtraction, unless you make the subtraction of all combinations of different phases. Now, we consider the application of viso-selective labeling. The typical way of viso-selective labeling in pulse ASL is applying a spatially selective inversion slab to the target artery as an angulated sagittal or coronal slab. The advantage of Picasso labeling is its flat, zero-effective, non-labeled area and steep transition to the labeling. However, because it is not selective in the inferior-superior direction, it often results in unwanted inclusion of non-targeted arteries. In fact, in pulse ASL, it's not quite possible to label only intracranial carotid artery without touching the common carotid artery, which also supplies to external carotid artery. So these images were acquired by using Picasso. In Picasso, the labeling plane needs to be planned perpendicular to the flow direction. To produce vasoselective labeling, additional in-plane gradients are applied, which produces a phase difference in the direction of the gradient, resulting in a sinusoidal-like pattern of the inversion profile. However, it should be noted that as compared to the inversion profile of pulsed ASL, the transition between the labeling and the control conditions is less steep. Also, because of the cyclic nature of the phase change, the control condition is not very flat, which could cause labeling of non-targeted artery. However, the shape of the inversion profile depends on the ways of applying transverse gradients. For example, by changing the transverse gradients from bipolar to unipolar, the control condition becomes less pointy, which is beneficial for vasoselective angiography. Additionally, in the unipolar transverse gradients, as shown in the right-hand side, the shape of the inversion profile changes with the Picasso labeling parameters, particularly in the maximum gradient and the mean gradient. It is important to optimize the shape of the inversion profile to achieve the narrow labeling target, flat, zero effect control condition, and sharper transition between the labeling and the control to minimize unwanted labeling of untargeted arteries. So it may sound a little complicated, but once the optimization is done, the planning of the vasoselective labeling in Picasso will be more reliable. Velocity-selective ASL is also used in ASL angiography. The advantage of velocity-selective ASL is the blood spins are labeled within the large imaging volume, which means the labeled blood can be created much closer to the distal arteries. I will be giving a presentation Thursday morning on an abstract titled Angiographic Comparison of Different Velocity-Selective Labeling Modules directly on cerebral arteries. So in this study, the MSDE with adiabatic refocusing pulses, such as a double refocused hyperbolic tangent, DRHT, or a 8-segment B1 insensitive rotation per 8, and the Dante pulse string, as well as the Fourier transform-based velocity-selective saturation, FTVSS, and the inversion FTVSI, were compared as a VS labeling module implemented before acquisition. An important point here is that the separation of the arterial and the venous signal. In this study, a spatially selective inversion pulse was applied almost a second before the label control module to new venous signal inside the imaging volume. The conventional VS labeling like DRHT has a nude zero gradient moment and a non-zero first gradient moment to be velocity sensitive. In contrast, the acceleration selective labeling has zero first gradient moment but a non-zero second moment, resulting in dephasing of spins based on acceleration or deceleration. So in this study, it shows a comparison of artery-vein separation based on velocity and acceleration. The velocity-dependent preparation resulted in quite overlap of arterial and venous signals. However, the acceleration-dependent preparation was quite successful to provide complete separation over a wide range of flow sensitizations. Here is an example of an intracranial AVM. X-ray angiography shows a small nidus, a feeding artery, and a draining vein. However, time of flight failed to visualize any components of AVM, presumably because of complex or slow flow. In contrast, acceleration selective ASL was successful to visualize all three components, providing very similar images as X-ray angiography. Finally, in the last few minutes, I want to talk about the scan time of ASL angiogram. ASL dynamic angiography has an excellent flexibility to achieve high spatial and temporal resolution. The advantage of ASL dynamic angiography is the data acquisition can be segmented to achieve high temporal resolution and repeated until the K space is filled for the desired spatial resolution. This is something the contrast-enhanced dynamic MRA cannot do. However, to achieve a high spatial resolution, the scan time becomes long. In 7 previous studies of non-vasoselective dynamic angiogram, the scan time ranged about 5 to 9 minutes. Here, an important point is the entire scan time is used to acquire data to fill a large k-space without signal averaging, which means when you are considering to obtain vasoselective angiogram, for example, by using HARDMAT vaso-encoded Picasso, you don't get a free lunch vasoselectivity, unlike perfusion imaging. In angiography, the scan time of vaso-encoded Picasso increases proportional to the number of applied vaso-encoding. So, the use of acceleration techniques would be a good option. Fortunately, ASL angiography is well suited for undersampled reconstruction, such as compressed sensing, because of its high sparsity. A previous study has demonstrated the compressed sensing with the magnitude subtraction shows a superior performance on ASL dynamic angiography as compared to the other compressed sensing with the complex subtraction or applied before subtraction. Additionally, vaso-encoded dynamic angiography has even higher relative sparsity than non-vasoselective ASL angiography, which allows the use of even higher acceleration. This study shows there was no significant difference in image quality between vaso-encoded angiography and the scan time matched non-vaso-encoded angiography. And the scan time matched non-vaso-encoded angiography despite the fact that vaso-encoded ASL require a factor of 2 higher undersampling. Moreover, this study also showed the smoothly varying arterial blood signal obtained by a high temporal resolution of dynamic angiography could allow further regularization of reconstruction. So in summary, ASL is not only for perfusion imaging. For ASL MRA, it can provide dynamic information with high temporal and spatial resolution. It can do vasoselective visualization and with no background static tissue signal and unwanted signal suppression by venous saturation slabs. So while making the ASL MRA sequence, Picasso, Paso Picasso, VSASL, acceleration ASL are all suitable for different applications, and strategies for reducing scan time need to be considered. Okay, thank you.